Hello, Broad Concept here again, and today we're going to start a new series that will contain elements of physics, biology, chemistry, and engineering. Hopefully, you will be able to make all the nitty-gritty connections between various elements from different blocks of science. So we're going to start with atoms. Basically, it's the smallest element, right? Everything is made out of atoms. Rocks, air, liquids, organs, people themselves, and even the very computer that this recording is made on. So essentially, the word atom comes from Greek, and in free translation, it means non-dividable part. Now, as we go throughout the video, we're going to put some definition words, and in the description you can find the link to the dictionary. Hopefully it may inspire you to look a bit further beyond today's episode. So earlier we've mentioned that atom is the non-dividable part. It's not actually entirely true, but that is a topic for a different episode. All you need to know at this moment is really what the atom consists of. And each atom consists of the same elements. So we have positively charged protons. We have electrons that are negatively charged, and we have neutron that does not have a charge. So we can find proton and neutron sitting in the center of the atom, forming nucleus, right? And it is worth to remember that name because you will find that name a lot of times in different blocks of science. Now, the electron actually orbits around the nucleus. However, it does so fast that on occasions we say that it forms a shell. Now, each orbit has a very strict amount of electrons that can be placed. So essentially, you can imagine a moon orbiting Earth or solar system and the planets orbiting the sun, and you can use that analogy to think of it as the atom. So in the center we would have a proton and neutron, and on different orbits we have certain numbers of electrons. So as I was mentioning earlier, on each orbit we can have a certain amount of electrons. So on the first orbit we can have 2 electrons, on the second we can have 8, on the third we can have 18. Basically it follows a very simple equation, 2 times n to second, where n is the orbit number. So for example, if I want to find out how many electrons I can have on the 4th orbit, I would have n as a 4, so 4 to second, that gives us 16, and times 2, that gives us 32. Okay, so not surprisingly, with all those different atoms with different numbers of electrons and different number of protons, at some point someone had to come up with a system that actually would make a sense of it. So Dmitry Ivanovich Mendeleev has come up with this periodic table that put the atoms accordingly to their weight, and he published his table in 1869. Here we have an example of such period table. If you look closely, actually it is in German, but that is not really that much of importance. Basically, if you know the important rules, you can read any table, any periodic table, regardless of the language. So here we have a close-up of the table. Obviously, as I was saying, it is in German, but anyway, let's try to decipher what it says. So let's pick zinc, number 30 on our table. We have a symbol of the element in top right corner, Zn in this case. On the left hand side, left top corner, we have the atomic number, and basically what it says, it states the number of protons within the nucleus. Now also somewhere in the middle of the box on the left hand side we have an atomic mass, and also below that we have the arrangements of electrons on certain orbits. So in the case of zinc we can see that on the first orbit, as expected, we have 2 electrons. On the second orbit, again, as expected, we have 8 electrons. On the third one, again, as expected, we have 18 electrons. And quite importantly and interestingly, on the last orbit, we have only 2 electrons. Now, that last orbit will become quite significant later on. Okay, so let's do a quick recap. We know what the atom consists of. We have a proton, we have a neutron in the nucleus, and we have electrons in various amounts on the respective orbits. So here we have a couple of atoms, some of the common ones, very needed for our body to function. So we have oxygen, nitrogen, we have calcium, we have hydrogen with only 1 electron, we have magnesium, we have iron. Obviously there's way more, but what we are interested in really is the last orbit of each atom that we have. Basically we call those orbits or shells, we call them valence shell or valence electrons. So again, it's another word that you will hear very common, and what it means is that an electron on that last orbit is an electron that is very lightly bonded with the atom. In turn, it means that it doesn't need much to either change its energy state or basically go away altogether from that atom and, for example, be accepted to another atom, right? Now, that is quite important because that way we can create ions and we can also make bonds, and also we can make various molecules from the atom themselves, from various atoms themselves. Okay, so we have our imaginary atom with 2 electrons on the first orbit and 1 electron on the second orbit. Now, any electron can change its orbit or energy state, but has to get some energy. Also, any electron can actually move out of the atom and potentially be accepted by another atom. And to do that, it needs a certain amount of energy as well. Now, those energy levels are precisely outlined by a specific orbit. So basically, each orbit has a specific energy state that the electron has to stick to. Now, how the energy can be given to an electron? Well, basically, we can use a photon, and that should already ring a bell because in nature, plants are using sunlight to get that energy. So basically, if the photon hits the electron, like we see on the animation, the electron can either change its orbit or it can be moved out of atom or bounce off the atom altogether. So we know that the electron can actually leave the atom. Now that will mean the number of protons within such atom is higher than the number of electrons remaining in the atom. And we'll call such situation, or we would say that the atom has now become an ion. And because it's a positive ion, we would say that it is anion. Now, if the situation is reversed, so say the electron has been accepted to the covalent orbit of the atom, then we will have a situation where there's a higher amount of electrons than the protons within that atom. And we would say that that is a negative ion, or in other words, cation. Now, those two names, anion, cation, or anode and cathode, actually used quite common in different parts of science, but that's a subject for a different video. So thanks to those relationships, thanks to the difference between the different ions, so negative and positive one, the atoms can actually kind of glue together, or in other words, they can bond. So we have three types of bonding. We have ion bonding, and probably you can figure out what that is. We have covalent bonding, and we have hydrogen bonding. So here we have example of ion bonding based on sodium Na and chlorine Cl. So sodium has one electron on its most outside orbit, and chlorine has 7 electrons on its most outside orbit. So that means that the sodium is quite happy to give away 1 electron, and chlorine is quite happy to accept 1 electron, since the maximum permitted amount of electrons on the most outside orbit, on the covalent orbit, is 8. Once that's going to happen, we will have a sodium atom with the overall positive charge, and we will have a chlorine atom with the overall negative charge. And as we know, the opposite charges attract each other, so those two atoms can join together, forming a molecule. Covalent bonding is slightly different, because basically we tend to say that the electrons or shells are shared by all the atoms, or partially by all the atoms involved in the molecule. So here we have a molecule of methane, and we have 1 atom of carbon, and we have 4 atoms of hydrogen. Now, how it all sticks together? So carbon atom has 4 electrons, but on its most outer covalent orbit it can have 8 electrons in total. Now that means that it is quite happy to accept another 4 electrons, and it does so accepting the electrons from hydrogen atoms. In turn, hydrogen atom on its first orbit can have maximum of 2 electrons, so it is quite happy to accept 1 more electron from the carbon atom, and by doing so the equilibrium, or the equal state, electrical state, is maintained between all of the 5 atoms involved. So that is why we said that in the covalent bonding the atoms or shells are shared. Now we're going to leave the hydrogen bond for the next episode. For today, that's all. Subscribe, leave your feedback, and see you next time.